This is the first of maybe just two short recordings that introduce the idea of probability calculations. And we'll be asking you mostly to do probability calculations for the results of crosses and for individuals in pedigrees, the chance they have a certain genotype. But we will be looking at things like tossing dice and flipping coins because I think most people instinctively have a good feel for how that kind of probability works, and it's really the same when you're dealing with a pedigree. So, you toss a dice, a single die, and there are 6 possibilities, and each of the numbers that could come up is a 1 in 6 chance, right? And it's kind of the same with a pedigree. If you have a certain cross, there's, maybe there should be 4 different outcomes, 4 different combinations of gametes that would give you 4 different possibilities, and then whatever proportion of those is one outcome would be your probability. The same general idea. So we'll go through that. And there are just, I think a lot of people are intimidated just because we're kind of multiplying fractions and there are these numbers and things. And I think the key is if you understand how the genetic crosses work and then you know how to apply 2 fairly simple rules, you will be fine. I know that some people, it's just even the fact that there are numbers involved that make it a little bit intimidating. But it really isn't as bad as you may think. Some of you are very comfortable with it too, so not everyone is worried about it. So basically, you just, as long as you understand, in a particular cross what the possible outcomes are and the likelihoods of different genotypes, you should be okay, because the rules are just 2 simple rules. There is the product rule, which is the calculating of the chance of 2 or more events that happen together. So you toss 2 different coins. Coin number 1 comes up heads and coin number 2 comes up tails. Those are 2 different events happening at the same time. So you would take the probability of the first and you would multiply that by the probability of the second, and it would be a half times a half, right, is a quarter. Now, depending on the kind of question, you may have a way of checking your answer, and I'll show that in the next example. So the second rule is the sum rule. You add up the probabilities when you're trying to figure out the probability of one or is the key word here, another event happening. So the chance that you toss a coin and it's either a head or a tail. In that case, you would add up the probabilities. So you add them. 1/2 chance of having a head or a 1/2 chance of having a tail. And a good way of checking for that, especially if you're asked for, what is the probability of this event? What is the probability of this event, this other event? For this, we know there are only 2 possibilities, right? It's either a head or a tail. And so when you add that up, it should equal 1, because 1 is the equivalent of 100%. So unless something very strange happens, when you toss the coin, you're going to get a head or a tail. Those are the only 2 possibilities. So this is a kind of a demonstration of the correctness of that approach. Okay, product rule. So this is the product of probability, of independent events occurring. That means the probability of one event doesn't actually affect the other one. So if you have, one baby born and then the next, maybe 2 years later, there's another baby born and the first one was male, there's no way the male baby doesn't check, or the baby that is coming doesn't check to see if a boy has already been born and then decide, to be a girl instead, that kind of thing. Each of the children, they have their own genes, they have their own X or Y chromosomes or whatever they are, and so they're independent. They don't depend on what the other event was. Okay, so those are independent. And then whenever we see and, what is the chance of this and this happening, then we multiply, right? So I'm going to go through this one. If you roll one die, and you it comes up a 4, there's a 1 chance out of 6 that that's going to happen, right? On the second one, there's a 1 in 6 chance of that happening. And so we're going to multiply those, and we're going to get 1 in 36. So there's a 1 in 36 chance. Now you can convince yourself this is correct if you like by writing out every combination of rolling a pair of die and seeing, you know, you could get 2 1s, you could get 1, the first one has a 1 and the second one has a 2, first one has a 1, the second one has a 3. You could write out every possible combination, and you'll find that there are 36 combinations, and that this is just one out of those 36 combinations. So this is, I can't remember why I put this here. No. So basically you use this when there's a chance. You could have several events. You could have 3 die or 5 coins, a chance of getting all 5 coins coming up 2 heads and things like that. But you always multiply those 2 probabilities, right? So you might want to take a look at these questions and do them. We'll do some of it in the class, in the lecture. But just think about, you know, what is the probability that both coins will come up heads? What is the probability of both tails? Probability of 1 head and 1 tail, and then the probability where the coins are specified. Notice that these are not worded the same. So you might suspect that the answers will be different, and you would be right if you suspected that. And I'm going to put this up here. This is the best way to figure out probabilities like this, where you figure out what is the chance of this option, this one, and this one. You can fill in those probabilities because these are the only options that could occur. They should add up to 1. That's a good way of checking that you've done these calculations correctly. And then you can use that to go ahead and answer these questions. And as I said, I'll have a couple clicker questions, quick ones, in the actual class where I ask you to give me the answers to these questions. And then do actually think how this is connected to a Punnett square, because, you know, this looks a lot like a Punnett square if you think about it. Okay, and then the sum rule. When we're talking about 2 what we would call mutually exclusive events occurring, then we add their different probabilities. So the probability of this occurring or that other thing occurring. Mutually exclusive is a term that you probably have heard before, but if in case you haven't, it means if one happens, the other one can't happen. So if you toss that coin and it comes up a head, it can't be a tail, right? We would call that mutually exclusive. If an individual has genotype small g, it can't have a different genotype. So if you're asking for the probability of having this genotype or this other genotype resulting from a cross, that would be mutually exclusive, because if the individual has one of those genotypes, they can't have the other, right? You only have one genotype. I hope that's clear. And heads and tails, going back to something that's really familiar, they're mutually exclusive. Okay, so the probability of getting either a 4 or a 5 when you, either a 4 or a 5 when you roll a dice, you're going to want the probability of this, the probability of this, and then you can use that. You can use that to calculate this. Okay, and I'll be asking that in the class too. So this is your chance to do some advanced prep, and if you have done, then you'll find it an easier time in the lecture. Okay. Now sometimes you use both, but for the product rule, it's focusing on 2 things that both occur that are not dependent on each other, and so we use and I always I have this in my head because and then I have the multiplication sign, and then if you're focusing on mutually exclusive outcomes, more than one of them, then we add those together. So the or is the plus, right? And again, here is a lot of questions we're going to require that you use both of those rules, right? And so in this case, so you throw two dice, and you're asking, what is the chance that I will either get 2 4s or 2 5s when that roll comes up? So you figure out the probability of this, which has already been calculated. You can figure out the probability of that, and then you will add them together to get the probability of 2 4s or 2 5s. Okay, now so that's some prep and some thinking about just general probability. And I want to move to talking about genotypes now and how you would use it in a particular cross. And so it starts with it starts with not making typos in your lecture slides. There we go. Where you can figure out probabilities in one example would be similar to what we talked about towards the end of lecture 9, I believe it was, where you have a particular cross, and you have 2 different phenotypes in the offspring. And for one type of phenotype, if you see that recessive phenotype, you know exactly what the genotype is. There isn't any question at all. But in a cross like this, these individuals are all going to look the same as each other, but 2/3 of them will be heterozygous and 1/3 of them will be homozygous. And we did some some kind of laborious clicker question stuff to go through the thinking about that. Whereas with a cross like this, when you see if we know that these guys are heterozygous and these guys are the homozygous recessive type, when we make the cross for recessive, again, we always know the genotype, but the dominant individuals that we see are going to be heterozygous because we know based on this cross. And for this cross too, homozygous dominant cross to homozygous recessive, all the progeny are going to be heterozygous. So these are cases where if you know the genotypes of parents, you can sometimes know for sure what the genotypes of offspring are, but there are going to be cases where we don't know for sure on a pedigree if an individual is heterozygous or homozygous, and in that case we would have to use these kind of probabilities. We wouldn't use 1/4 and 1/2 because we know that they don't have the homozygous recessive, so we're only thinking about the ones that have the dominant phenotype, and of those, 1/3 will be homozygous and 2/3 will be heterozygous. In the case of X-linkage, the good news is if we see males and the trait is an X-linked trait, then we always know exactly what their genotype is going to be. Okay. Because there's only the one allele, we don't have to worry about being heterozygous. And depending on how the cross is done, just like in the previous one, depending on how the cross was set up, if we know what those parent genotypes are, then we know exactly what the genotypes of the offspring are. But in a case like this one, where individuals in the progeny, in the offspring, that have one dominant allele but could be homozygous or heterozygous, then we have to resort back to probabilities again. And so in that case, it's fairly straightforward. In a cross like this, these females, half the time, they always get the dominant X-linked allele from dad. Half the time, they get mom's recessive allele, and the other half of the time they get mom's dominant allele. So there's a 50-50 chance of them having either the homozygous dominant or the heterozygous genotype. Okay, and I'll just finish with this. This kind of repeats a little bit what we sort of went through in lecture 9 at the very end, which we actually did on Friday. And so this is just watch the wording of the question. So if you're asked, like, this cross has been made, Heterozygous yellow individuals, this is the peas, yellow seeded peas, and heterozygous yellow peas. And the plants, those plants have been crossed to each other. What is the probability that we'll see, homozygous yellow allele in the progeny? And it'll be 1/4. So it'll be a 25% chance. So if you had all the peas in a big bag that had been produced by that cross, and you just closed your eyes and you picked one out, there's a 1 in 4 chance that the one you picked out would be homozygous dominant. And so this is for before the offspring have been produced, or before you know anything about them, before you've looked to see what color, for example, the peas are. Now, if the peas are green, the probability of being homozygous is 100%, or a probability of 1, you could say. The probability of being heterozygous is going to be 0, because you can't be heterozygous and have the green phenotype, right? So we can be very precise with our probabilities in this case, because we know exactly what the genotype can be. It's only one option. It can't be anything else. But if you have a big pile, a big bowl, say, of the yellow peas, then these are your 3 possibilities. One of them is homozygous, and 2 of them are heterozygous. And so this gives us the probability of being homozygous among just the yellow peas is going to be 33%. Probability of being heterozygous is going to be 67%, or 2/3, right? And I'm going to stop there, because I think that lays all the foundation for then looking at a couple of pedigrees, which I expect will take the bulk of the time for lecture 12.